So in the previous video, we discussed about resistive model. In this one, we'll talk about Thevenin model. So continuing where we left, import PyBaMM, PyBaMM.models.fullbatterymodels.equivalentcircuit.all. So we can see that Thevenin model is already present and we can directly utilize it from the model options. Similar to the previous videos where we called the DFN model from the lithium ion library. Here we'll call the Thevenin model from equivalent circuit library. So we can set it to a variable model equals to PyBaMM.equivalentCircuitModel.Thevenin. And then let's also print what are the model options available. So we have calculate discharge energy set to false by default. Diffusion element is also set to false. Operating mode is set to current. Number of RC elements is set to 1. This code it's just for reference, not for the exercise use. So here we are just trying to see what are the other modes available. So the default mode is current, which we'll continue with. But for other applications, there are also possibility to use voltage mode for, let's say, constant voltage charging, power mode for defining drive cycle loads or real world driving scenarios, and then also other modes including resistance, CCV, etc. There are a bunch of different modes available to choose from. For now, we'll continue with current mode. Within PyBaMM, we have the option to also update these parameters. So let's see if we set this number to 2, and the way we call it is similar to what we do for typically defining models. Instead of having a blank parenthesis in the end, we insert options, use the keyword options, and then use the keyword which is present within the dictionary, number of RC elements, and then set it to a defined desired value. So we do options equals to curly brackets, number of RC elements, and then colon set it to 2. And then we'll print the model options again to see if it's updated or not. So you can see here it's 2 where it was earlier set to 1. So this way you can play around with number of RC branches and also add more if needed. For most application, 2 RC branches are sufficient and gives very good accuracy. In applications where you expect a lot of nonlinear transients and would like to capture it to a very uh, small tolerance, then in that cases 3 RC branches might be sufficient. In absence of data, you can also start with 1 RC branch. So in this scenario, we'll keep it simple and bring it back to 1 RC. Now let's talk about circuit parameter maps. Circuit parameter maps include similarly defining the grids and the maps. So we'll define SOC and temperature grid with similar resolution, 11 data points resolved at 10% SOC or 0.1 fraction SOC, and going from 0 to 1, and temperature ranging between 283 to 313, which is basically 10, 20, 30, 40 degrees Celsius. OCV map is again set as a 44 data point array. It's a 2D array. Each row represents a given temperature, and each column element represents the SOC grid. Additionally, we'll have R1 and C1 maps being defined as well. So we end up getting 4 maps and 2 SOC, 2 grids, one for SOC, other for temperature. In practical cases, even a third dimension could be introduced, which includes current. With change in current, these responses also vary, and it's recommended to have current as the third dimension to get the most accurate results for practical or commercial purpose. Next, we'll define temperature in degree Celsius to 25, Q equals set to 2.16 ampere hour. Next up, we will call the model, which is the PyBaMM.EquivalentCircuit.Thevenin model. And similar to what we had for lithium-ion battery, where there was libraries of parameters or database options available like Chen 2020 for NCM chemistry and the Prada 2013 for LFP chemistry. Similarly, in case of equivalent circuit models, we have ECM examples. ECM example which has some predefined values which can be a starting point, and then we'll also do some param update later on. Firstly, let's print all the parameters which are exposed in the model which can be tuned. So for that we do a for loop for p in model.parameters print p.name. We end up getting a list of 10 to 15 parameters which includes OCV, R0, R1, C1 maps along with some temperature dependent quantities affecting the thermal model like entropic change, which affects the reversible heating or heat generation. And then we have cell thermal mass, initial temperature, etc. We'll not go into the details of other parameters, but we will stick to updating the circuit parameter maps in this exercise. We'll probably talk about the other ones in a later video. So with that, let's define these maps. Now, there's a function which can be very handy in such scenarios. It's called the lambda function. And the syntax might be hard to remember, but can be easy to read. So this lambda function helps us reduce multi-line code of doing an interpolant to just a one-line code for doing not just interpolation but also extrapolation. So the way the syntax works is you define the OCV map. This is the final output, which is the interpolated function. And then we write the keyword lambda, define the input. So the input OCV is just a function of SOC. It doesn't have temperature variation in this case. So we will have just one 1D function here. SOC is the input. And then we use colon PyBaMM.interpolant, define X and Y, temperature grid and SOC grid, define the Z value, which is OCV map, then define the inputs, which would be temperature. It's a constant, so it's not defined here. And then we have SOC as the other input, which will be solved dynamically using Coulomb counting technique in the hindsight by PyBaMM. And then finally, we set the extrapolate to true. Now, within PyBaMM, although we had the maps defined just as a function of temperature and SOC, but still it accepts R0, R1, and C1 maps as a function of three variables, temperature, current, and SOC. So for the case of avoiding any errors while running the simulation, we have to define the same format. So it's lambda t I SOC and PyBaMM.interpolant, which pass on X and Y, define R0 map, give the temperature and SOC operating conditions, and set the extrapolate to true. And then do the same for the remaining two maps, R1 and C1 as well. Once this is done, next step would be to update the parameter list, the default parameter list which we saw earlier. So for that, we can do param.update and then set all the capacity values to Q, which is 2.16, initial SOC to 0.999, just to avoid any current noise which might overshoot the SOC beyond 1 and cause the simulation to stop. So just as a factor of safety, we'll start with slightly lower value. Then we have OCV set to the OCV map we defined here using the lambda function. And similarly, R0, R1, C1 maps being updated here. Next, we'll define the experiment. So we have experiment equals to PyBaMM.experiment, and as we have discussed earlier, it uses plain English to define the experiment, which will be discharged at 1C until 2.5 volts. Then we'll set the simulation, sim equals to PyBaMM.simulation, define the model, define parameter values, experiment, and then finally solve. So we have sol equals to sim.sol. By default, it will solve at 1C for 1 hour or until it reaches 2.5 volts. We'll run this, and then next step would be to define experimental data for time, SOC, and voltage, which is defined here. Then we'll extract the values of T, V, and SOC for plotting purpose. So we do sol, call the time variable. This is the keyword for time. This is for voltage, and this is the one for SOC. And then we store the entries in these variables. And finally, we use matplotlib to plot simulation and experimental results. So I forgot to run this one before moving to the next one. Sorry for slight debugging required there, but as I reran the code, it gave the right results. So we can see here simulation and experimental results match pretty well for both voltage and SOC. And this is how we model Thevenin model. And just a quick recap. ECM models can be classified into two types, resistive and Thevenin. Resistive by default is not available to be, so we derived a pseudocode where we calculated voltage as a function of OCV minus I times R naught. R naught and OCV were defined as maps. 2D maps as a function of SOC and temperature. Current was derived using C rate and capacity. And SOC, since these maps are a function of SOC and temperature, in this case, temperature was fixed, but in a future study, we can also make lump temperature model where we can solve for a linear differential equation to extract temperature. And you can easily find some codes available online to, or images, Google images to find the solution of a first order linear differential equation, which will be basically used to solve the temperature relation. I was able to just quickly find one image which I'll paste here. So this is basically the equation which is solved. MCP dt by dt equals to minus T naught by R Thevenin plus Q dot. This can also be represented in the form of convective heat transfer. And for that, let me try to quickly find that out. Okay, I got the right equation. Sorry for that. So this is kind of the equation which is solved for lump thermal model, which can also be integrated with this code. So MCP dt by dt equals to Q. Q is the heat generation, which can be a sum of the I square R loss plus the entropic heat or the reversible heat component. And then this is subtracted with HA delta T, which is basically the convective heat transfer based on the cooling strategy being used. For a forced cooling, H will be higher. For a free or air cooled system, this H value would be lower, and accordingly, the temperature rise will occur. And this can be rephrased into a 1D linear differential equation, which can be solved easily with analytical solution. Then we basically looked at how to do Coulomb counting to find out the SOC at every time step, and update the SOC so that it can be fed as an input along with temperature to the lookup maps, and then finally plotted simulation and experimental results. This was using purely primitive or empirical relation based solution. On the other hand, Thevenin model is existing option available in PyBaMM, so it can be accessed from the equivalent circuit library. And the Thevenin model can have multiple number of RC branches, which can be defined with the options. You can define the maps, use lambda function to easily interpolate, then finally update the parameters, define experiment, can also define some drive cycle experiments here, HVPC, GITT tests, which are more suited for such applications to identify whether one RC or two RC is required. A HVPC test can be more handy with multi C rate level pulses. And then finally, we added experimental data and compared and got some good correlation. Although this was a constant current discharge, but for RC branches, maybe HVPC test or GITT test might help look at the transients more effectively. So I hope this video was helpful. See you in the next one.